Okay, so after like 20 or 30 minutes running, we can look at the result. And if you double click the 2D FET now, check here, you can find there are several results finished. So if you look 2.7 to 3.7, that means these results are finished. The last one is not finished because last one, the program when you change to a BIOS, new BIOS, it was saved before it run. It will save the temporary memory, and then you will continue to run, and finish you will overwrite the temporary file. So usually the last one is not the data you can look at. You just look at, except if it's finished, then the last one is valid. But if it's still running, the last one is useless. And if you have finished more BIOS simulation from here, you need to double click this to refresh. Otherwise, you will only have hold. Okay, let's look at the BIOS port condition. First is that let's look at the IV curve. So IV curve, let's say we apply the Gen BIOS. So you can plot Gen ID, VDID. Okay, then if you plot, you could. Okay, you can see this IV curve. All right, and you will find it's negative because ID in ID current is flowing out, and yeah, leave the surface. The IS is current is flowing in. So usually, if you want to change your sign, just plot ID ISVD, then you can get the normal IV curve you want. Is that okay? So this is
What's IS? S is
source. If you plot IG, you cannot see anything because you didn't use IG. So the current of IG is 0. So usually you plot IDVS. So this is IV curve. And you can plot just electron current or whole current individually. So if you plot electron current, hold down of IS, yeah, see it's almost overlapped, and ISP, yeah, ISP is 0. Why? IS is N-type contact, so that's not whole current. So ISP is 0. ISN has a value. And the same way is that if you plot IDN, you get some value. And if you plot, hold on, you plot IDP, you get another value. So you can find that you see some leakage current. Do you see that? You see some electron current here, but this is a real whole current. So there's some leakage current flowing to them.
Which one is the whole current here?
Well, let's keep remove. This is whole current.
This is whole current.
Okay.
And
hold on.
And
IDN. Yeah. Then you see the leakage current. Okay, you can find out usually leakage current is like we discussed. Leakage always fast happen in certain BIOS port. Okay. Alright, so this is ID, and if you look at IQE, then we say ID IS total IQE. Okay, so this is IQE curve. Okay. Okay. So remember, this is a 2D simulation. So the current density unit is M per centimeter. M per centimeter. So you can either change to total current amp, or you need to change it to current density, because amp per centimeter is not used to. So here we can do normalized 2D current. The chip width is 0.015 centimeter. So we can normalize the current. So the unit become amp per centimeter square. So this is the right unit. So you need to do normalization. Just remember. Okay, then this is the real scale of current and the range. So remember to normalize the current, otherwise you will be misleading. You will think the current density is so usually is smaller. If you don't normalize, amp per centimeter, the range usually is from 0 to 10. 10 is already a very high current density. So it's like this. Okay. So this is the IV, IQE. Then if you plot IQE, IS total, hold down, non-radiative, OJ. Okay, you can plot straight together, and then you can find that it's not a very beautiful line. It's because we didn't calculate too many points. Okay. Alright, so we can go back to look at the FET. Let's say at 3.0, plot EC. The thing is normal, just like this. Look at here, contact is here, and the contact is here. There's a field in this direction. Okay. Then if you look at, most importantly, we'll look at radiative recombination rate, because it tells us where the electron and hole recombine laterally. Okay. So if you plot out the radiative recombination rate, see, it's very important to watch here. It's almost current clouded under P there. Okay, it's very crowded. That's all the current crowded here. So actually, if you say the current density is 20 amp per centimeter square, the actual current density could be 200, because all the current is crowded in this area. If you say this is like 1/10 of the area, so the actual current density here is like 2000. If it's 200, it's like 2000. If it's 20, it's like 200. So the current is very crowded. Of course, because we don't put ITO. We only put P-GAN. So you see a very strong crowding. So right now there are two solutions. One is put ITO. The second is that they call free chip. Free chip is like the whole top layer is the P-type contact. And then we spread the current through the N-type. So we make the N-type as conductive as possible. Make N-type like ITO to make current vertical injected. Okay. So radiative recombination usually will watch, and then we can also watch the current. So you can look at the current density. Okay. Maybe we need to plot low scale. We don't. Oh, sorry. We need to choose 3.0. Here, current density file. Choose the right voltage. Okay, so this is log scale Jn, and you can find that current actually is flowing down and then spread out and then going to this. But this is electron current, so electron current should be 0 in the P layer, so it should be blue. But you can see some green, that means there's a huge overflow here. Not huge, it actually is log scale. So there are some degree of leakage current. Okay, this is a log scale. You need to plot the log scale, otherwise. And usually, if you want to see clouding, you will need to plot JNY, not JNY, because JNY decides how current going up. JNS is current in this. So if you have current clouding, you still see here that all the current is the same. It's not look like clouding. So usually plot JNY. And if you plot JNY is like this, you can say that the current mostly down and then spread out to here and up. So it's something like this. This JY. JY usually tell you the real information how current clouded. Okay.
You see here that it's looking like this?
Yeah, it's something like this. If you check the sign, you'll find that this is absolute value. Because log scale you cannot plot negative value. So if you check the value, you'll see that there is a sign here and another sign. For example, if this is negative, then this is positive. So it's something like this. And you plot JNX, you will find there are huge current along this direction. So actually you can get something like this. Okay? You need to think about that. It's not so easy to, but if you look at for a longer time, then you will get familiar how to interpret this data. Okay. Then what else? What information else you need? Let me see. Recombination is usually we will look at, and the non-radiated and the OJ usually is the same as rate. The distribution usually is in the same because they are all carrier density dependent. So usually the distribution is the same as radiative. So you can plot the radiative. Sorry that the log scale looks not working. And you can plot the non-radiative. You can see it's almost the same. OJ almost the same range. And okay, the landscape is here. U of EC, U of EV, and the U of EV2.
Oh, these are the landscape.
Yes.
Okay.
1 over U. 1 over U. Okay. Temperature, we're not generation, trap, EFN, EFP. That's all the same definition like 1D. But the distribution is just like 2D. And you also can plot along S and the Y. So everything clear? Okay, so the simulation is finished. So we should see the complete IV curve now. IDVS. Okay. And then you can find that the shear resistance comes in. Then in 2D simulation, it's not going to infinity. It will saturate a certain line. It's like the shear resistance. Okay. All right. Okay. So if If there's no problem, let's set up how to set up an ITO. ITO is very hard to set because ITO actually in reality ITO is an N-type layer and P-GAN is a P-type layer. So actually, when they put together, it's forming a tunneling junction, like electron tunneling to. But tunneling junction actually usually is not supported well for most solver because you need to tune the band-to-band. If you remember yesterday, I told you there's a band-to-band tunneling parameters. You need to tune the factor. So here we assume ITO to be a equivalent P-GAN layer, but with ITO's conductivity. Do you know what I mean? We assume a layer is the same as the P-GAN, and usually we say ITO is conducted by N-GAN, but we say it's conducted by P-GAN. But this P-GAN is not the real P-GAN. We use impurity. Impurity to force they have a certain amount of hole density, and we set up a certain fixed mobility. So we let the shear resistance to be equal to ITO. Shear resistance.
So we're going to add P-GAN layer, but we are going to change the doping level?
Yes. So how to do it? I have a parameter code. If you choose here, you can see that I set up something like a virtual TCO P-GAN. So eventually, if you choose this, and you generate parameters, let me change to example 2. You can find that the program automatically generates a layer that impurity is this value, and this two is I set before, so this should be removed. Usually we won't set anything here, but if you in the beginning, if you generate you something like this, and they give you a fixed impurity, and the mobility is 2000. So this value is from what I work with some epistyles, their ITO's property. So I generate a equivalent. This is not bad ITO, like a conductivity is like 3 times 10 to minus 4. Resistivity 3 times minus 10 to minus. You can calculate. Actually, you can calculate by yourself. You know the carrier density because these are fully active. So you know the carrier density and the mobility, and then you can calculate the resistivity. So here we set up a whole mobility like 2000, and the carrier density is 1E19. But you can set up the carrier density to be minus 1E20 and the mobility to be 200. I mean, it's the same thing. Do you know what I mean? But what I would suggest is that you just keep my setting and change it slightly, because in our experience is that if you put a very high current density, high carrier density, the convergence speed is slow.
Okay.
It's a numerical issue. If you put a lower carrier density with higher mobility, the convergence speed is faster, but they give you the same result because the resistivity is the same. So usually you put this, but I should not put in the layer 9. Do you know what I mean? Because layer 9 is P-GAN. So we need to add one more region called ITO region. So how to do this? Let me load the program ES1. Okay, then I call it ES2. We need to add one more layer. Is that right? So we need to go back here, mesh setting. We need to add one more white point. So ITO layer typically 50 nanometers or 100 nanometers. So I'm going to add one more point. So I say 11. Okay. And you can find that there's one more point appear here. So I say if it's how much? 100 nanometer.
For the layer? Yeah.
So it's 4.31, and I want to be bumped.
Yeah, if you put 100 of ITO, your LED will release nothing because ITO is highly absorbent. ITO is highly absorbent, so it's not more in the range of 10 nanometers usually.
ITO for blue is not so bad.
Okay.
Laser is probably bad, but it's still the transparency is still like 90%, so it's not so bad. And this, oh sorry, I should choose bump. Okay, 2e minus 2.1e minus 4, 2e minus 4. Sorry, I need to choose bump, ratio 1.1. Okay, ITO actually, okay, we can make the ratio larger. Okay, to save our speed. Okay, actually like peak layer, we can also make ratio to be larger to save our time. 1e minus 4, 2e minus 4. Okay, so you can see that the green number decrease because peak layer actually there's no, usually electric field is not so large, so we can put a larger ratio. And if I also want to save time for EBL 1.4, yeah, 2.001 e minus 4, 2.0 e minus 4, actually the same. Alright, so actually the only quantum well region, just keep the ratio to be small. Yeah. I mean close to 1, not small, close to 1. Okay, so we get one more region, and then material range setting. Don't forget one thing. Empty section. If your empty section, for me it's 4.4, so I'm fine. But right now it's
4.31.
Yeah, so you need to make larger empty section. Don't forget this. So you can check you always need to check real mesh. Okay, so just check real mesh to see if any problem. Let's plot the mesh. Okay, looks fine. So let's go to material range. Material range, we need to change the region number to 10. Okay, so we have one more range. So 4.31, 4.21. Finish. Okay. Then finally, add one more layer, and then finally in the base parameter general region, we have this one. Okay. So we choose the virtual TCO gain and the generate parameters. Okay. But just remember one thing is that when you generate parameter, everything will be reset except doping. So we change the tau n. Do you remember that we changed the tau n here? Don't touch the tau here.
Okay.
Because that's a heavily p-type. We want the carrier to be recombined in the contact. So we put a very short lifetime. So don't do anything here. But here, just remember change to 5e minus 8. Okay, let's check if doping is changed. Looks like okay. Set back to table. Okay, so let's check range setting, prod range. Okay, just check if everything is covered.
For the ITO, is it virtual TCO/P/other or
This one, let me show you. Choose virtual TCO pgan. Pgan is because I don't want to discuss the polarization difference between one material and the gain nitride. I just make the concave perfect. If you simply put additional material by yourself, then the polarization charge, gain nitride has polarization, another material doesn't have polarization. You make a bending in the contact, and that could cause some trouble. So if you choose ITO P other, then the polarization will be 0. If you choose ITO P gain, it will set the same polarization as P gain, so they avoid. Anyway, this is an artificial layer, so there's no special physics. Just want to represent the resistivity, equivalent resistivity to the ITO.
The non-radiative tau is 5e negative 8.
Yeah, except it don't change this.
one.
Yeah, don't change this one.
I remember yesterday you about the electron mobility and low mobility. You change just, I think on the second top layer, you just make some smaller electron mobility just for convergence or something like this.
Which one?
I think it was yesterday. I'm sure there is just 2 layers that change the mobility.
Oh yeah. Here pgan, I change the pgan mobility to be. Here I change it to be maybe 5 or 2.
Yeah, it just.
You can change or not. I mean, it depends on the experimental. If experimental say 2, then you change it to 2.
Okay.
If it's 5, then you change it to 5. 10 is very common value.
It's a common.
Yeah, but it's not heavily doped. Very heavy. It's not under very heavy dope condition. So.
Okay.
So in sometimes you will heavily dope, as heavy as possible because you don't make good contact. So then your mobility decrease.
Okay.
Yes. So you should always change. I mean, mobility. I just tell you, mobility is something you are responsible, not me. So you need to change by yourself. Tau should not. Tau is the non-radiating lifetime tau. Tau should not using default because it depends.
Yes.
And the B usually don't change too much, so you can use default. OJ depends on what OJ you finally decided. Otherwise, effective mass should be fine. Yeah. Dielectric constant you don't need to change. Yeah, so the most important is mobility and the non-radiating lifetime tau. Okay. Alright, so if everything is okay, save project 2 and we can run another case. Okay, so let's see, we can look at some result to see if our setting is right or wrong. So remember, now the file is ES2, so go to ES2, okay, and 2D ES2, let's choose, I finished 2.8, so I plot 2.8. So some mistake you have made is that you choose the wrong TRI file. For example, if I plot this, it still can plot. Look, and look there's no problem, but actually there's some shift. This TRI to the null point, there will be some shift. It doesn't have problem here. Why? Do you know why? Because we only increase one layer. So the missing point, it just says there's no point. So there's no problem. But if you use ES2 and I plot ES1, I think we will have some problem. No, see, you cannot plot because you have more point in the mesh file, but you have less data point in the structure file. But anyway, we can go back to what we are going to see. I think the most important 2D is the radiative recombination. Okay, so you can find the radiative recombination now is spreaded. So can you find that the density is very uniform now, and we can look at the current. Because I'm not sure 2.8, the current density probably very low, so it's not maybe not the right indicator, but we can still we have more data now. Okay. Alright, you can see that the current spreading is good. And let's go to larger BIOS is more accurate. 3.0. Okay, looks good. Radiative recombination. Okay. So you can find there's a little bit darker here and lighter here. So there's a current clouding here. So if I plot here, you can find a clouding point change to this point. Because ITO to N-gain, the shortest path is go through ITO, then to N-gain on the right. So the current clouding becomes here. And if you go to even larger BIOS, let's see how much we got now. Okay, 3.3. Okay. This is log. Is that log? Let me double check. Okay, this is linear scale. This is easy. So let's go to radiative recombination. Okay, you can find when you increase the BIOS, the clouding becomes more serious. But its clouding is not under the P-GAN layer. The clouding is go to end of ITO, because that's the shortest path for current. So if you continue to increase the current, the clouding will become more serious. In our experiences, it will be clouded, start to cloudy on the edge, and become more and more cloudy when you increase the current density, even when you have ITO. Okay. Is that clear? Alright, so we gave you two examples. One is with P-GAN, only P-GAN, and the one is P-GAN with equivalent ITO. And you can calculate the IV, IQE. Let's check IV. IV of this case. Okay, this is the IV, and we need to normalize to be 0.015. Okay, this is the IV curve, and you can compare the old data to the new data. So this is old data, this is new data. So
Did you compare the two?
hold on.
Hold on.
Hold on is a super function. You can compile everything together with the hold on version. Okay. So I think this is the old data because there are more BIOS points, and this is new data. So you can find with ITO the resistance decrease. So you see a beta curve goes up. And the IQE, you can plot IQE versus IS for the first case, hold down for the second case. So the droop becomes better. It's there's less droop with ITO because you don't have very serious current crowding. So you didn't see very serious droop. Okay. So droop will depend on the crowding. It's very typical. I think usually we don't discuss in 1D simulation, but actually in 2D it's very clear that if you change the content, then you change everything. What's it?
But I forget to change the name
Why it's not?
of the project, so I think it's just that mix the two.
Yeah, to isolate. Is that right? Probably it's just what do you plot?
Oh, it's the DDCC.
QE.
But if you go to the
So QE will have some problem because you will mix two data.
yeah, even the DIV has an issue. I think it's very. So yeah, you see details.
Yeah, it's like two data combined.
Yeah.
No, not really.
Yeah.
Yes, exactly. This.
For the IV.
It don't overwrite the file. Probably you just
Yeah,
merge it.
yeah, you
It
merge.
merged the file, yeah, it doesn't overwrite. Okay, so yeah.
So yes, and you have the two. So you have.
Do you know why we don't override? Because usually you won't override IV and QE because usually in our real case is that we want to make a lot of simulation. We go to different nodes.
Yes.
And all the nodes data we just collect into one file, and then we do the sorting,
Okay.
and then run different BIOS range. We can make the speed faster. So if you want to run new data, you need to change the name.
Okay.
If it is the same data, then you will merge the IV and the QE. So there are two same points. And so if you are smart enough, you can separate them. Because you can see there are two trends, so you connect by yourself. Then you know which one is which. Yeah. The data one is, if you open the raw data, the data one is the new data. Okay? Working?
Okay.
Hope so. More mistake will be made in 2D.
Why do you think this happened?
You didn't change the lifetime. A coefficient. Tau n, tau p. Your two case, tau n, tau p is different. Usually. Because we changed the tau n to 5e minus 8.
Yeah.
But maybe you didn't change in the first case, or you didn't change in the second case. So you will see the peak change a lot.
Okay.
Because your tau n, tau p is different. I guess.
Maybe he has
Other same one, you forgot to change the name.
Oh yeah. Yeah, if you save under another new name,
Your project name need to be changed.
change the name.
Otherwise, you will not
override.
There are two things you can do. If you want to clear, if you want to clear the previous data, you need to click save, run, and clean all data. If you don't do this, save and run, you will override. I mean, it's not override. It will cover, merge.
But if you change the file name.
Yeah, but if you change the file name in file, you have also to change the file name in its project name.
You need to change project name.
Yeah, you have to do the both. If you change here, that will change the
You should change this first, and then save.
Yes.
Don't don't change the name in the set because it's only changed here. This one is not changed.
Right.
Yes.
I
So you
didn't
still
think
run
about
the,
that,
the old data.
Might
So
be-
usually,
You have to make the mistake once.
yeah, you need to
It's
change.
very
You need to change at this
That's what happened
position.
to me yesterday.
Yeah.
Right?
You made once and
Yeah,
after
so you'll never happen again.
Yeah.
Maybe.
Yeah.
I just told him that the purpose for this is that we can run on different computer with the same input and the same home directory, so they will merge all the data in one folder. So in the IV, you can run in different computer. If you want to make a lot of points, for example, you run 10 points, it take 20 minutes. But
Yes.
if you use 10 PC, you still take you 20 minutes for 10 points. So you can merge 100 points
Yeah.
with 10 PC. But of course, it usually works in it only works if you want to merge, then it means that you are working on a cluster environment. You have a home directory, same home directory. But if you run on different PCs, different things, you need to merge by hand, by your hand.
Yeah.
So is this software like faster than Silence or the same? Silence is only 1 day. 1 day? Oh, okay.
I remember that 1D we are faster.
1 day.
We are faster. I don't know if you used, you can compare.
I'm not using much.
The E3 in the department I went, they have a Silence, and for the same node point, it's not fast. So that's why I described on the Monday. I say that because it opened the effective quantum potential, so we guess he solved the eigenvalue, so it's not so fast.
And the program chooses by itself the cluster numbers, or you have to specify them. If I have four clusters on my computer, or does the program choose by itself? Oh yes, I have 4 clusters available, or it just
No,
takes two,
it's
or-
you need to do everything yourself.
And how we do this? How we do this here? For example?
You want
Because
to run in 4 computer?
Oh yeah, for example, I have my computers. I have four clusters inside, and apparently you use only 1 or 2. So if I want to use the 4,
Then you just run this on 4 computer.
So
You want to submit job?
No, I think I don't have the correct word. It's not clusters. It's
It's a 4-core process.
Core, yeah. Yeah, 4 core.
Poison.
Yeah, in my computer.
You guys did that in the code, I think, with parallel.
Paralyze it. Yeah.
Yeah, it's not automatic.
Like, does it support parallel computing basically?
It support multi-core,
Yeah.
but not MPI. MPI is that you submit a job to different computer, but the same job, and they run parallel in different computer. It doesn't support this,
Yeah, okay.
but it support if your computer have a multi-cores, you will use multi-core to accelerate the speed. So
Okay.
So it'll do that.
Automatically.
yeah, I'm done. Right now, for example, if you are running, you can check the CPU usage.
Yeah, it's not full.
currently.
It could be usually like 50%.
Oh, okay.
Because if you have one core, that's if you have 2 cores, 4 thread, you can only use 2 cores.
Okay.
It's the
physical,
problem
it's-
of CPU, not the problem of my
Okay,
core.
it's physical core.
Yeah.
Not virtual core.
Not
Okay.
threads.
But you can run 2 programs at the same time. It still use 50% of 2 thread. You can
Yeah.
use 4 thread.
Okay.
Do you know?
Yeah.
All program can only use 1 thread of 1 core.
Okay.
It's not the architecture problem.
Yeah.
Because Intel has multi-thread means that if a 1 core 2 thread, that means if they have another job coming in, they can let them run in the parallel. But these two actually there is no sequential,
Yes.
so they cannot run. If you have 8 thread, 4 core, you can only do 4 core parallelization. You cannot do 8 core. That's a limitation.
Yes. Okay.
So you always see 50, but if you have 8 cores, you still see 50. If you have
Yeah.
16
So
cores,
just
still.
take the graph.
Yeah. Am I still wrong? Actually, if I wrong, okay, if you check,
Deux cartes physiques, 4 chats. En fait, il peut utiliser qu'un chat de chaque. Donc, en fait, il peut utiliser plus qu'un chat de chaque carte physique. Donc, en fait,
can I check?
Et ensuite, on finit le truc, en fait, tombe 25.
Okay, if you check the CPU usage, in my computer I have 4 CPU, and you can find that it use almost 50%, but the usage is very strange.
Yeah.
But it's use multi CPU. Yeah. And if you run different job, you can go to different CPU computer to run different job. And the process for your PC is that you do the same thing first. But if you go to the supercomputer center, you can submit job.
Okay.
Submit job means that you generate an input file and use their command to submit the same job. No, not same job. Different input
job.
file, because you need to define different BIOS range. So you generate, like if you have 10 computer, you generate 10 different input file and then submit the job to the 10 different computer. So you can run 10 jobs at the same time. That's when you have a cluster environment. If you don't have that, then just do what you are doing now.
I think we do that.
Huh?
I think we have a cluster going on.
I know for the MRI you have to ask, they have to approve what you want to do.
Yes.
Usually they will approve. Okay. Like when I was in Michigan as a student, I applied the account. They just give me an account, but with the lowest priority. That means you can submit job, but you need to wait.
Yes.
If there's something empty, they will let you run. And if you ask your professor to pay for some money, then they give you like 10 workstation. You can always have a 10 job, no matter when you are going to use. But if you don't pay, then you just wait. Okay. So in this case, this is a new. I just bought this laptop. Look guys, it's CPU usage is good. We have 3 CPU used. Overall. Okay, 70%. I got 70% usage. So that means the new architecture is good, isn't it? Oh, I can go into 3.4G. That's a turbo boost. Yeah? I remember that he told me that turbo boost is 3.1. How you go to?
You have some yes.
It's 2.7G, and he told me turbo boost going to 3.1G.
Yeah.
But right now it showed
3.
3.
You have the overclock. Yeah, the Intel core you can overclock them when you are pushing on computers.
Overclock.
Yeah. Yeah, so you
Automatically overclock.
Yeah, I think the configuration.
But I remember he said the overclock can goes to 3.1.
Oh yeah.
But right now it's 3.4.
Yeah.
It's gonna burn a hole in the table.
Okay, anyway, so I don't need to run because it's finished. And okay, so I think time is up. And we didn't introduce ray tracing. Probably we can. Do you need ray tracing in the future or no? I guess not.
La ray tracing est juste tool.
So maybe not needed. Here the ray tracing is very cheap scale. The difference is that we can only model ray tracing in this geometry, and the light extracted from this chip will depend on where it recombine. So if you have a recombination distribution like this, high here, low here, then the light, when you start to run the photon, they will, depending on the distribution probability, then they will, if you have more carrier recombination here, they will generate more light to starting from this point. And you also just run this charger. So if you want the whole packaging is not working here, this is only for chip light extraction, chip scale. And I can introduce some special function like empty session. There are many things to play. This is a square, and actually, let me show you another thing. Is if you empty session number is 2, okay, and okay, you can choose rectangular f1 equal to 10, f2 is y button equal to 1, and f3 extra equal to 20, and to 2. Okay, then you choose periodic along x, then they'll ask you the periodic number like 5, and the spacing is like 20. Okay, if product structure you can make something like this. Okay, and if you make a real mesh, then you can check how the real mesh looks like. It's just like this. So you can make any special structure you like, but sometimes you'll get problem. For example, if I give you empty section, I tell you this is the triangle. Triangle we need 3 points, so we say 10, 10, 1, and 21, and 15, 2. Okay, if you plot structure, it's like this. But if you make real mesh, it's not good. It's because your mesh, look here, your mesh density here is bad, so actually you got some problem. You cannot really cut it well. So if you want to make spatial, you need to tune your mesh to be a good shape.
You need probably to add some X node and Y node to refine the mesh.
Okay, just tell you this. And for light extraction, if you want to make if you know what I mean, for light extraction usually have a texture surface here, so you can use empty to make a texture surface.
Okay, you have to extract it.
Yes. You can also make a texture surface here on the top, if you can make it. For example, like here. Okay, if I change this to be 4.2, 20, 4.2, and this to be 4.4. Alright, so we make a real mesh. So we plot the mesh. You can see that we make a surface structure like this.
So it can come from like undercut.
Yeah. But you need to check if the mesh is good. I mean, sometimes the mesh is very dirty, like like the second case.
So if it's like dense enough, you'll be fine.
Usually,
And you can use Gmesh.
Huh? Oh yeah, you can.
Which should be able
Yeah,
to
yeah.
deal with that much better.
Another one is that mesh setting here. We can choose use Gmesh. Then all these functions are disabled. If you click to use Gmesh, all these things will. Then you need to click.
Open G.
You need to load
Okay.
load a mesh file. For example, if I don't know if this mesh file is working or not, but I can load it and the plus structure. Okay, this is the structure made by Gmesh, and the 9 number list. There are many 9. 9 means you need to go to meet. This is 9.1, 9.2, 9.3. I don't know which one is which because I forgot what kind of mesh this. And the service number 18. You can click. Sorry. Part. Make. Sorry. Plus structure. So if you use Gmesh, you can click. They'll tell you this is region 18, this is region 31, 16, 35. And then you need to assign, then you assign the parameter by region. Gmesh, they have a definition of region number, and each station they have their region number. And if you use 3D, they call it volume number. Surface number and volume number. Volume number in 3D we need surface number and volume number. In 2D we need line number and surface number. Because surface number is for assign a material parameter. Line number is for assign a content. For 3D, surface number is for assign the content. Volume number is for the material. So the concept using Gmesh is like this. But actually, I don't like to use Gmesh. Sometimes I don't like to use Gmesh because Gmesh, like this, is a good mesh. This is called finite, transfinite mesh. The mesh is like my mesh is very uniform in XY direction. But sometimes Gmesh will generate those kind of random. It's very random mesh. So in this kind of mesh, usually we got some problem to plot the electric field. It becomes like a vibration or something like not very good, especially for semiconductor transistor. It's not good. For heat, for flow, this kind of is okay, but or strength is okay. But when you use for the carrier transport, usually it's vertical and lateral. Then if you have some mesh like a variation in this, then the plot is very dirty. So 2D, I won't suggest to use Gmesh because most feature you can use in our built-in mesh can be done already. So it's more easy to control. So you can use Gmesh, and Gmesh is like if you use Gmesh, then material range here you need to use Gmesh range. Okay, so we need to change this 0 and the Gmesh range like 20. I don't know how many range. So you ask it that what's the 20 region, the volume number equivalent to which one? And after setting this, then you define contact. We say 3 contact, so you need to give the contact Gmesh boundary. If I say 4, then I need to assign which is the line number. And the line number, for example, I say 9.4 equal to drain contact, 9.6 equal to source. Sorry, it's something like this. Okay, so everything setting, then the third part is the same. The third part, if you define, actually this is a repeat, it's not good, you know. You need to assign each by yourself. And then basic parameter, you can just depend on 20 regions. Can you have more? I mean, if your range is overlap, it's okay. For example, you can set up the whole region to be A material, then second region to be covered here, and third here, fourth. So the rule of this setting is that in the range material parameter setting, the later one cover the previous one. That means the region number 1 will be covered by region number 2 if there's overlap. For example, if you have a material like if you want to make a square and the inside is another square, the way you could do is that you plot 1, 9, 1, 2, 3, 4, 5, 6, 6 region with the square. Do you know what I mean? Because if you want to assign each section, you can have first square and separate 3 square, and so you need to 5 region.
1, 2, 3, 4, 5.
Yes. Okay. But the other way is you just set up 2 regions. One is the whole range, and the one is the smaller one.
Okay.
That's equivalent to what you did.
If they're in the right order.
But the order should be right. Otherwise, if you set small first, large second, then everything will become large.
Will overlap the small.
Yeah.
Makes sense.
Yeah. So the sequence, there's some meaning of. If there's no overlap, it's fine. If there's overlap, the sequence is very important. The later one will always override the
This is
first
G
one.
mesh. Just normal.
Normal condition, no matter it's G mesh or not. For example, you can choose G mesh. We have 20 region, but G mesh only have, for example, 16 region, but we still can set up 20, and you can do this meaningless things. You choose 4 region to be 16. So the program finally will use the last one. Do you know what I mean? You will just automatically cover everything. So it's just writing the code. There's a for loop, and then you check that. Okay, if this is in here, then you change this, and then the second region check if it's here, then change. So if it's changed, then override it. So it's just like this rule. I don't make the check, so if it's overlap or not, because I think it's. If you check this, then like the case I just mentioned that you need to cut enough region, then it becomes not very convenient. Okay. All right. So 2D have some other function like parameter setting. Usually you won't do anything here. This is just the basic part, but you can use spatial density of state. You can use trap, Gaussian trap. Usually we use Gaussian trap. We don't use trap. Gaussian trap is the trap density is like a Gaussian distribution, and trap is like a delta distribution. And the Gaussian distribution is much better. I mean, no matter in reality or no matter in convergence, it'll give better imperialization. And also ray tracing is here. Okay. And the transistor setting is like you can define a field dependent mobility. If you in the future some people use calculate hand. Generation setting is for solar cell. And the spatial function, they are all disabled. This is very special, that generation only for electron. This is for the future probably work for the called the infrared photo detector, like the quantum cascade laser or something like that. You only absorbed in the electron, but there's something need to be fixed. I mean, additional term. But somebody requests me to generate only electrons, so I build this function, but but I don't think that will be right at this point. And thermal setting, let's change. Maybe there's a bug here. Thermal setting it would be, thermal setting would be for the solving the heat, and you can solve the thermal problem or iteratively with the Poisson DD. But you need to this one is working. These two I need to tune. I'm still working on this. Okay. And
does it take into account the conduction, or does it take into account the, for example, the radiative or the so the radiative we don't care, but
yeah,
the
I need to write more interface like how to define the temperature dependent mobility and how to define other things.
okay.
Lifetime is temperature dependent or something.
Okay, yeah, okay.
So right now it's you can directly solve the thermal problem, but don't iteratives.
Okay.
But anyway, the heat function, if you are not familiar with that, just don't try at this moment. And I will also change the interface. I'm trying to make it complete. OLED is for the OLED that calculate acetone diffusion and field dependent. OLED has a very special field dependent mobility. Usually semiconductor mobility is when you apply larger field decrease. In OLED is the increase. You have a larger field, the mobility increase. Of course, it won't go to infinity, but it's already very small, but it increased to more close to semiconductor. So it's a very special feature, but this one is finished, but I don't think you will use it. Okay. So these are the functions of 2D. You can keep in mind if one day you need some of them. Okay. All right. So